Hello, everyone. Welcome to this Quarks webcast. My name is Samantha Chan. I'm a software developer at the IBM Toronto lab. Here with me today, we have Queenie Ma. She is also a Quarks contributor and a developer from San Francisco. And we have Kendrick Wong and Mary Colmore. She's a software developer from the IBM Toronto lab with me. We have two very exciting topics for you today. So first, we're going to hear from Queenie. She's going to give us a tutorial on how to develop a Quarks application and deploy it on a Raspberry Pi. And then about a couple of months ago, Mary, Kendrick, and I participated in a internal hackathon. And the goal there was that we want to leverage Apache Quarks and the Watson Insight for Weather API. So we designed a water conservation application for that hackathon. We're going to demo you with that end-to-end application and show you how we actually build it. With that, I'm going to pass the presentation to Queenie. And Queenie, you're on.
Let me share my screen. Okay. So, hi, my name is Queenie, and I am an Apache Quarks contributor, and I work at IBM. Today, I will show you how to write a simple Quarks application and get it running on a Raspberry Pi. First, I will go through these steps to register a Raspberry Pi with the IBM Watson IoT Platform Cloud Service on Bluemix. Then after, I will give a brief overview of how to set up a Pi and install an operating system on it. Then I will show how to properly set up the Quarks development environment on your local machine. And finally, I will give a demo where I will walk through an application that sends CPU data to the Watson IoT platform and show the running application in action. So here is the overview of the architecture diagram. So on the left, we have a Raspberry Pi, and we will get an Apache Quarks application running on it. And that application will send a T-stream of JSON objects containing some CPU data to the IoT platform in the cloud. And we will be able to view that data in real time in a browser. So the first step is to register with Watson IoT platform, and it is a service on IBM Bluemix. There's a free trial available for that, so you can sign up for that. And once you have the service created, you can launch the platform dashboard. So right now, I will show you how to register the device. So this is the Bluemix dashboard, and this is the service that I'll be using. Okay, so right now I have no devices and no device types. So I will start by creating a device type, and I will name it Raspberry _ Pi. Give it a simple description. And you can also provide some optional attributes, but I won't be doing that now. Okay, now that the device type has been created, we can create a device of type Raspberry Pi. So I'm going to name it Queenie _ Raspberry Pi. And the service gives you an option to either have a authentication token automatically generated, or you can provide one yourself. I will provide one, and I'll simply put my name and click Next, and here's the summary of the details that you've provided. And so now it shows you these 5 properties, and you will need these to connect from the Raspberry Pi to this platform service. So let's keep these properties in mind, and I will go back to the presentation. So once you see that screen with the 5 properties, you need to create a device configuration file. In this case, I just named it device.cfg and saved it somewhere on my local machine, and include these 5 properties. And we'll be saving this file for later. Okay, so once you've registered, next thing to do is set up your Raspberry Pi if you haven't already. The Raspberry Pi Foundation's website has a wealth of information and resources that can be very helpful during the setup process, so I recommend checking that out. First and foremost, you need to install an operating system on your Pi, and the most recommended is Raspbian OS, a Debian distribution. And the easiest way to install that is through Noobs, and Noobs is an installation manager that includes multiple operating systems. If you bought a Raspberry Pi kit, it usually comes with a micro SDHC card with Noobs pre-installed. But if that is not the case, the software is freely available on the website. Once you have installed the OS on your card, just insert it into the Pi, as well as the necessary connections to a keyboard, mouse, HDMI cable, to an external display, and an Ethernet cable. Then boot up the Pi and pick an operating system to install. The process will take a few minutes to complete. So once your Pi is booted up, you should see your desktop, and we can now start setting up your Pi to work with Quarks. To build Quarks, there are only a few steps we need to take, and it is assumed that you are running Java 8 and you have the Apache Ant build tool installed. So at a bare minimum, Quarks requires 3 jar files, which can all be easily found through simple web searches. The project uses JUnit as a Java testing framework and JCocoa for Java code coverage. So after you have downloaded these jars, copy them to your to a directory .ant/lib based off your home, and that's so the Ant build file knows where to find these jars. And once that's done, we can proceed to download the Quarks source code. So I'll show you the GitHub repository. So Quarks, the source code is hosted in a Git repository, but there is a GitHub mirror, and there are 2 ways to download the source code. So there's either you can download the zip file of the latest code, or you can fork this repository and clone your own fork. And that second method will allow you to pull in the latest changes from developers. Okay, so for this demo, I just downloaded the zip file to make it easier, and I've already done that. And it is this master.zip, and I unzipped it into incubator quarks-master. So if I go into that directory, the next step is to compile Quarks. So to do that, you just run ant in this top level directory, and what that will do is build the jar files, generate the Java classes, and generate the Java doc. And the jar files that we will need for the application live in this target directory here. Okay, so let's go back to the presentation. All right, so the application I wrote is hosted in my Eclipse IDE, and as I mentioned before, you need a Bluemix account, the IoT platform service, and you need to have your device registered in that service. So the application we will be writing is fairly simple. You'll take a device configuration file as an argument and use it to connect to the Watson IoT platform service. It then creates a stream of sensor readings, which essentially uses the Pi4j Java library to retrieve the Pi CPU information. So this application does not require any external sensors, which makes it easier to get started with Quarks. But in the next part of this presentation, the use of a real sensor will be demonstrated. So after generating tuples, the app then sends those sensor readings to the cloud, and we can view that data in real time. So that's the overview for the application, and let's start writing it. So here is my Eclipse environment. I have already created a Java project and the class. So before we start writing anything, we need to set up the build path and include the external jars that the application is dependent upon. So we have 6 that we need. There's the Pi4j jar, which you can find on their website. That's used to retrieve the CPU information from the Pi. And these 5 other jars are available in the target directory that I mentioned earlier. Okay, so once you have that set up, let's dig into the application. So the first step for any Quarks application is to create a direct provider, or actually a provider. And this a provider is an object that contains information on how and where your Quarks application will run. And a direct provider is a more specific provider, and that runs your application directly within the current virtual machine. Oh, I forgot to mention, this is the device configuration file we created earlier, and that's specified as an argument. And we will use that in the next few steps. So after the provider is created, we can create a topology instance, and that's a container that describes the structure of your application. So where the streams in your application come from and how the data in the stream is modified, if at all. Then we establish a connection to the Watson IoT platform service. So we use this IoTF device class, and to connect, we need to specify the device configuration file with the 5 properties. Next, we create a data source which generates a stream of sensor readings. And in this case, we read from the sensor every second, which is indicated by these 2 arguments. And let's look closely at how we can generate each tuple on the stream. So I've separated that into a separate method here called system info. So to create this continuous data stream, we utilize this topology.pull method, and we can specify what each sensor reading or tuple will look like. Watson IoT requires that data be sent in JSON format, so we specify that each tuple on the stream is a JSON object that consists of 3 properties. So the first property is the time, and the next 2 are CPU temperature and CPU voltage. So to get these 2 properties here, we use the Pi4j library, and it has a system info class that contains numerous methods to obtain system level data about a Raspberry Pi. And that's all it takes to create the stream. And every second, 1 JSON object with this structure gets created. Now going back to the main method, here's where the magic happens. The ultimate goal of this application is to send data from a Raspberry Pi to Watson IoT platform where you can monitor its state. And this line does that. So using the IoT device created here, we can send device events to the cloud and use the stream, the reading stream that we created. And in this case, we use the fire and forget quality of service, meaning that we send each tuple at most once. So after we send those tuples to the platform service, we can print the stream to system.out, and I did that for debugging purposes. And finally, the last step of a Quarks application is to submit the topology to the direct provider. All right, so this is all running on my local machine, and what we want to do is get that on the Pi. So to do that, I can export this application as a runnable jar file here. But first, we need to generate a run configuration. So all you need to do is just click run as Java application, but it will fail because we do not provide the device configuration file argument. But don't worry about that. We will get that working once we have this application on the Pi. So we can export the jar file and select the class IOTF Raspberry Pi sensor and provide a path to save the jar file to. And in this case, I selected package required libraries into generated jar, which means that the third-party jar files will be already included in the generated jar. So just click Finish. Okay, and to get this to your Pi, the easiest method is to use a USB device, and I have already done that. And I have my Pi here, and I'm connecting to it through SSH. So here are the files that you'll need. You'll need the jar file that we just created containing the application, as well as the device configuration file. So this is the configuration file. Now all you need to do to run the application is java-jar, specify the name of the jar file, and the argument was the device.cfg file. Now it's trying to connect to the platform service. And here it says that we successfully connected, which is good. And these are the readings generated from the Pi. And these are the readings that are being sent to IoT platform. So I'll show you that these data points now in the service. Okay, so here is my device here, Queenie_Raspberry Pi. And if you wait a few seconds, these devices will show up here. So if you click on one particular reading, we see that it contains 3 properties: the time, CPU temperature, and CPU voltage, which is what we expected. And now we can use this to monitor our Pi from somewhere remotely, possibly. And so that is the application. And now I will be passing it over to Mary, and they'll talk about an application that they wrote.
Thank you, Queenie.
Sure.
Okay, so back in April, there was a hackathon at the IBM Canada Labs where the challenge was to write an IBM Bluemix application that uses the Watson Insights for Weather service to get weather information. We got a team together and we brainstormed a few ideas, and we decided that we wanted to use a Raspberry Pi with Quarks running on it to represent an edge device. And we also wanted to include the Bluemix streaming analytics service to perform some real-time analytics. This was obviously above and beyond what the original challenge called for, but we had lofty goals, and we knew that with the portfolio of products and services that we were familiar with, it should be fairly easy to achieve our goals. So we eventually decided on a water conservation project where our mission became to save the world one smart sprinkler at a time. So now, how often have we seen this? This is not smart, but it happens a lot. And there are drought conditions in many parts of the world, including California and the US, where water shortage is a real issue. The government in the affected areas are trying to conserve water by imposing bans or restrictions, but it is often difficult to enforce the bans effectively. And some people are simply rich enough or ignorant enough to ignore the bans. Freshwater crisis is a looming problem in many parts of the world, and irrigation for agriculture is a major contributing factor. Here are just 2 examples. The Aral Sea in Central Asia is almost dry, and the Colorado River in the US is dying. A majority of the water drained from these resources was used for agriculture, for irrigation. And if you do a quick search on the internet, you will see many more other scary examples of water crisis similar to this, all in different parts of the world. So we need to conserve water and be smart about how we use water. Having smarter sprinklers will help to conserve water, not only in the urban areas, but especially for agricultural irrigation.
There are smart sprinklers out there already, but they are not smart enough. We need smart connected sprinklers that are smart enough to perform local analytics to determine whether the local conditions require the sprinklers to be turned on, and something that can also connect to a backend system for more in-depth analysis. For example, to check for rain in the forecast and or government bans on water usage. Now, I'm not only talking about the sprinklers in the urban areas. We are also talking about those hundreds and thousands of sprinklers on huge commercial farms. Like farms across the U.S. spend hundreds and thousands of dollars for irrigation, for watering their lands. Having smarter sprinklers will help to not only conserve water, but also protect the bottom lines for farmers. So it's a win-win situation for everybody. So we set about building a prototype of our smart sprinkler using a Raspberry Pi. And I'll now hand it over to Kendrick to show you what we built. And then following the demo, we will show you how we built the prototype.
Thank you, Mary. So in front of you, you will see the brain of our smart sprinkler system. This is the Raspberry Pi. It's got three main components. Obviously, there's the moisture sensor currently in the water right now. There's the sprinkler control. For this demo, the sprinkler control has been replaced with an audible buzzer. So when it turns on, you will be able to hear it. The CPU itself is running Quarks and is connected to the Watson IoT platform via the Ethernet cable. An average smart sprinkler may be able to control sprinkler based on the moisture level of the soil. But this sprinkler that we have here is much more smarter than that. Whenever the Pi thinks that it should turn on the sprinkler, it will first send a water request to the IoT platform. Then the streams application will run a series of analytics and provide guidance back to the sprinkler. When it comes to the type of analytics that the stream application can perform, the possibilities are endless. But for this demo, we're going to show how it's using the weather forecast and governance data to make decisions for the sprinkler device. And we need a way to show what the Pi is thinking. So for that, we have a web dashboard application. And the sprinkler device is going to send a status to the web UI. And here, the web UI is divided into two parts. Well, on the lower part is where the sprinkler status is being shown. The blue gauge on the left shows the current moisture sensor reading. In the graph, there's two main lines, a red line and a green line representing the moisture threshold for turning on the sprinkler on and off. When a water request is made, you will actually see a dot on the running blue line. You don't see it now, but during the demo, you will see that. And there's also an indication when the sprinkler is on, represented by orange dot on the blue line. On the upper half of this UI, you will see a weather forecast. That's the weather forecast for the sprinkler location. For the purpose of the demo, we need a way to simulate the data, or the weather data. So there's this weather simulation which we can turn on to control whether the forecast should be sunny or rainy. You may also notice this water ban button just underneath. We will use that to indicate if there is a water ban in effect. So for the first scenario, we are going to simulate the weather data so that it's going to forecast sunny condition. Water ban is off at the current moment. So once I take the sensor out of the water, you will see moisture level starting to drop until it hit the lower threshold, at which time a water request will be sent. And because there's no rain in the forecast, we are expecting the sprinkler to turn on, and you should hear an audible buzzer. So I'm taking out the sensor from the water now. As you notice on the graph, the moisture level is slowly dropping because it's losing moisture. And once it hits the red line, we will see a green dot indicating a water request. In this case, because there's no rain coming, you now hear the buzz indicating that the sprinkler system is on. This sprinkler is going to turn on until the water level hits the upper threshold, and then it's going to turn off by itself. In the next scenario, we're going to show that what would happen if there's rain in the forecast. Obviously, for a smart sprinkler, we don't want the sprinkler to turn on when there's rain, and we're going to show that. So once again, I'm going to put the water sensor out of the water. The rain is going to come, but not yet. So the moisture level is going down. And as soon as it hits the lower moisture level, a water request is going to go. But this time, the sprinkler does not turn on because there's rain in the forecast. And as we have this rain simulated data, the moisture level is going to rise up again because it's raining. For the last scenario, I'm going to show how the water band is going to have an effect on real time on the sprinkler. So we're first going to turn the weather simulation to sunny because we do want the sprinkler to try to turn on and moving the water band to on position. I'm going to take the moisture sensor out now. As the moisture lowers, reaching the lower threshold, the sprinkler is going to ask for water request. This time, though, because the water band is on, it's not going to turn on the sprinkler. And you'll see a series of green dots indicating that the sprinkler is asking for water request, but because the water band is on, it's being rejected each time. Now we're going to show how lifting the water band in real time is going to have an effect. So as soon as I lift the band, the buzzer should go off right away. And we're also going to show that we can put the band on right away after that to turn off the sprinkler. So we're going to turn it off. The buzzer goes on, indicating the sprinkler is on. Now we're going to turn it back on, and the sprinkler would go off right away. So that concludes the demo part. If Samantha is going to show how this is implemented inside the Pi.
Thank you, Kendrick. So in the next session of the demo, I'm going to talk about how we have actually implemented this application. So first of all, we're going to show an architecture diagram. So we have the smart sprinkler, which is implemented with Quarks on the Raspberry Pi. This application will do the local analytics and basically continuously monitoring the moisture level in the soil. To talk to the back-end services, we have leveraged a lot of the Bluemix services that are available to us to get us up and running very quickly. So for us to connect and communicate with the back-end services, we are using the Watson IoT platform, which under the cover is running MQTT for the devices to talk to the back-end services. For back-end analytics and the business decisions on whether we are going to turn on the sprinkler or not, we use the streaming analytics service from IBM, which allow us to do real-time analytics with the data that is coming in and providing a real-time response to the data. For us to get the weather forecast, we use the weather company API, which is Insight for the Weather, which allow us to basically query the weather forecast in the next 7 days so that we can actually make a decision to decide whether we will turn on the sprinkler or not. And then for real visualization and actually looking at the data, we use the Node.js server on Bluemix as well as React.js for our web UI. So in the following so this is all interconnected. And in the following presentation, we are going to focus on two pieces of the application. So we're going to focus on the Quarks application design as well as the back-end streaming analytics application to show you how we actually did the back-end analytics. From the Quarks application point of view, the goal of the application is to do local monitoring of the moisture reading from the soil continuously. And as part of kind of a device, like when you're reading data from the device sensor, one of the problems is that sometimes the reading may not be very accurate. Sometimes you might get a spike, sometimes you might get a lower reading than normal. So for us to be able to get a more accurate reading, we'll calculate a rolling average of all of the current moisture level using a window of data. And we will not communicate to the backend services unless we have to. So we will only detect, if we detect that the current moisture level is too low, that's when we're going to send requests to the backend system to ask if we can turn on the sprinkler. And then as the last part of it is that the sprinkler would not get turned on unless the backend service has allowed us to turn it on or give us basically permission to turn on the sprinkler. In this diagram here, this is the architecture of the application. So at the core of it is what we call the sprinkler controller. The sprinkler controller simulates the current moisture reading as well as the sprinkler activity, which is the buzzer. For us to talk to the actual sensor on the Pi, we implemented the sprinkler controller using the sprinkler simulator with sensor class, and we go through Pi4j to actually work with each of the sensors that we have or the devices that we have. For the backend services, so all the readings we collect locally, and then for the backend services, we use Quarks to collect this information and send information to the Watson IoT platform. So next, we're going to kind of look at the code and see what we have done. So before we do that, we'll look at the actual physical setup of how we have hooked up the different sensors. So the first sensor that we've hooked up is the moisture sensor. So this is a picture of the moisture sensor. There are three things for you to hook up. So you have to hook up the power to pin 1, which is going to give you a 3-volt power to the sensor. And then we also hooked up it to the ground pin. For us to get the data out of the moisture sensor, you have to hook up the digital output of the sensor to the Pi. And I have hooked it up to pin 11 on the Pi in here. So what it does is, if the moisture is detected to be too low, then the digital output will tell you that the output is actually low from the sensor. And then if the moisture sensor say it's dry, then you'll get a high output from the sensor. The next thing we needed to hook up is the sprinkler or the buzzer. So this is very easy to hook up. So a breadboard here, and I hooked up the input to the buzzer onto pin 13, and then I also hooked it up to the ground pin to pin 6. So that's all there is to it from a circuits perspective. And now we're going to kind of talk about how we actually write the sprinkler controller. So to write the sprinkler controller, I created the sprinkler controller interface. And the job of the sprinkler controller is to gather the moisture reading from the moisture sensor, allowing us to control the buzzer on and off, and also control the rain simulation. For us to be able to get the moisture sensor reading into the Quarks topology, the controller needs to implement the supplier reading API. So it allows us to basically kind of provide a reading into the Quarks topology so that we can analyze it locally. In a lot of the examples that you will have seen in the Quarks community is that the example will show you how to actually create a topology that reads sensor information as primitives, so like double or floats. But on top of that, you can actually use a custom class to provide the sensor reading. So for me, I've created a custom reading class, and the reading class will provide information about the current location of your sprinkler, which is the GPS location, which I've hard-coded here, whether the sprinkler is on and off, and the current moisture level. For us to be able to use it in the Quarks topology, your custom class has to be a serializable object, so I have implemented serializable in the class so that I can pass it into the Quarks topology. So that's all there is to it, to the sprinkler controller interface. So after I've defined the interface, this is the sprinkler simulator with sensor class is the concrete implementation of that interface. So on top of that, we have 3 things in here from this class. So for you to work with a buzzer, you have to create a GPIO pin digital output object. And for you to work with the moisture sensor, you have to have a digital input object. And then for you to actually kind of interface with it, you have to create a GPIO controller, which is a class that is part of the Pi4j library. So before you can work with it or can basically call it, you have to provision these pins in your controller or in the application. So in the constructor of our sprinkler simulator class, what I have done is I have provisioned the moisture sensor to GPIO 0, and I have provisioned the buzzer to GPIO 2. One thing you will notice is that even though I've wired up the moisture sensor to pin 11 on the Raspberry Pi, when I actually provision it using Pi4j, I have to use a different pin numbering option. And the reason for that is that Pi4j follows an abstract pin number scheme from the Wiring Pi project, which allows the application to be more resilient to any hardware changes. So this is an abstract numbering. And if you look at the Wiring Pi project and how it maps to the Raspberry Pi pin convention, you'll see that pin 11 is actually referred to as GPIO 0 in Pi4j, and pin 13 is referred to as GPIO 2 in Pi4j. So this is why the pin numbering is set up like this here in the code. So now that we have provisioned all our sensors and be able to work with it, we are going to talk about how we actually get the moisture reading from the sensor. So as I have talked about before, in order for us to basically provide data into the Quarks topology, you have to implement the supplier reading interface, which is on the top left corner here. You just have to implement this get interface. And then in this method, we'll get the moisture reading from the sensor and then create a reading object and return it. And that's how you provide data into the Quarks topology. If you look at the get moisture method, this is the actual method that we interface with the moisture sensor to understand what the current moisture level is. So in here, I ask the sensor, is the reading currently low or high? And if the reading is low, then I know that there is enough moisture in the application. That's when I override the simulator to make it to return a really high moisture level. And if it's low, then we'll just kind of use whatever is simulated from the superclass and return that as the current moisture level. Controlling the sprinkler or the buzzer is also very easy. So I have a method that allows us to turn the sprinkler on and off. And so whenever this method gets called, we'll just set the pin state of the buzzer. So if the sprinkler is on, then we'll set the pin state to high, and if the sprinkler is off, we'll set the pin state to low. And that is easy. So now that we have set up the sensor and allow us to be reading from the sensor and controlling the buzzer, how are we going to use it in the Quarks application? So first of all, so this is the application that I have written. So first of all, I have created the smart sprinkler object. So as is in the screen here, I've created the smart sprinkler simulator with sensor object. And then I created the direct provider as well as a topology, as Queenie has shown us before. So you set up the topology for your Quarks application. And then I asked the topology to pull data from the smart sprinkler every second. So basically, whenever the data is pulled from the smart sprinkler, the get method of the sprinkler class get called, and then it will return a reading object from the smart sprinkler. And then that will create a T-stream of reading, which is the current reading of the moisture level. So now that we have the reading, we are going to try to calculate the rolling average of the reading. To calculate the rolling average, you have to do two things. The first thing you have to do is you have to set up a window, because data is flowing into the application continuously. So you have to have a window of data where you're calculating the rolling average for. So we created a window data calling the last. So given the T-stream of moisture reading, we call the last method from that T-stream to create a window. And then with that window, so this is a sliding window. So what that means is that we'll keep the last 9 readings in the window. And whenever a new reading comes in, the oldest reading will get discarded. And then also, whenever a new reading comes in, the aggregate method will get called. And at that time, we're going to look at the content of the window and calculate the average moisture reading from the 9 readings that we have in the window. So that is the code that we have done that. As part of this aggregate call, I also use the average reading to kind of decide if we have enough moisture in the soil. And if there's enough moisture in the soil, then I will turn off the sprinkler. And then we created a new reading object with the average reading and then pass it on to the downstream for further analysis. Now, the next thing we have to do is go, okay, now that we have the average reading, we need to decide if the current moisture level is too low. And if it's too low, then we want to send a request to the IoT platform and basically to the backend service to see if we can turn on the sprinkler. So this is the code that does that. So first, we call this filter method. So what is actually saying is that if the current average moisture reading is too low, and the sprinkler is turned off, and we know that there's no rain coming, then I need to basically ask to turn on the sprinkler. So this is the filter method will allow the reading to go through if that condition is true. Once it has gone through, and that means we have to make a request to the backend service to turn on the sprinkler. To do that, we'll create an IoT device, as Queenie has shown us, and I have just hard-coded the device configuration in here. And then because the IoT platform basically require to talk to the IoT platform, it is required that we send in our request as JSON object. So before we make the request, we converted the reading into a JSON object, and then we send, we call this events method from the device to send the water request to the backend. And that's basically the end of that topology flow. So if we go from gathering the moisture sensor information, calculating the rolling average, and then making the request. The next thing we want to do is, okay, now that we have made the request, we need to kind of go, are we really allowed to turn on the sprinkler, and how do we decide that? So the decision to turn on the sprinkler is done by the backend, and for us to actually receive commands from the backend, we call this device.commands method, which is going to get responses back from the streaming analytics service to tell us whether we are allowed to turn on the sprinkler or not. And then for each of the response we get back, we look at the payload of the response and see if we are approved to turn on the sprinkler. And if we're not approved to turn on the sprinkler, what is the reason why we're not approved? And then we react accordingly. So if we're approved, then we just turn on and off the sprinkler based on the response we get back. And then if we know that we are not approved, and we know, and backend, basically the forecast is telling us that it's going to rain, then we are just calling the smart sprinkler to schedule rain and make rain in the next 10 seconds. And the last thing you have to do to run this topology is submit it to the direct provider that we have created at the beginning. And then all you have to do with this is that you just follow what Queenie has shown you to export that application into jar file, and then I deploy it onto the Pi as is. So the next thing what we're going to do is Mary is going to take us through on the streaming analytics side to show you what we have done with the backend service.
Okay, can you hear me now? Good. All right, so Samantha showed you how from the Pi we are sending events to the device, and also she's waiting for commands back to indicate whether the sprinkler should turn on or not. We used IBM streaming. You can't hear me? Sorry, there's technical problems here. Oh, you can hear me? Okay. All right, sorry about that. So we are using the IBM Streaming Analytics Service to perform the backend analysis. So Samantha showed you how the Pi sends the event to the IoT platform service. Now to perform this request, we have a couple of streams application running in the Streaming Analytics Service, which will receive the event, perform the necessary analytics, and then that will decide whether the sprinkler should be turned on or not, and then we send that decision back as a command back again via the IoT platform service. IBM Streams has a number of toolkits available that makes it easy to write Streams applications, and these toolkits are publicly available for free in the IBM Streams GitHub repository. One such toolkit is the StreamsX IoT toolkit. This toolkit facilitates the writing of Streams application that integrates with the Watson IoT platform. The toolkit provides a pre-built, ready-to-run Streams application that takes care of the connectivity to the Watson IoT platform. The IoT toolkit further provides a publish subscribe model for independent streams application to subscribe to device events made available through this IoT connector application that comes with the toolkit. And when the application decides that it needs to send a command back to the device, it uses the same connector application to connect back to the IoT platform service and to send the information back. So what this means is that with the toolkit, it's easy to set up connectivity by running that pre-built application. And once we have that running, all we have to worry about is writing what I keep referring to as an independent streams application that will do the analytics. And you're not obviously then limited to a single analytics application. You can write as many to do as many analysis as you need to on the device events, on information that's coming from that device. Okay, so let me show you an overview of the Streams application that does the actual analytics. So I'm switching over to Stream Studio, which is an Eclipse-based development IDE for developing Streams application. I have a couple of projects here containing my Streams applications, and this IDE here also provides a graphical editor that allows me to construct a Streams application using drag and drop. A Streams application is made up of a number of operators that process the data as it flows through the application. So constructing a Streams application is as simple as dragging and dropping the operator that you want, depending on how you want to manipulate and process the data. And then you connect the operators to indicate how you want the data to flow downstream. The tool also provides this what we call an application graph view, which allows you to visualize the topology of your application. So, and each Streams, what you see here is actually 3 Streams application that we wrote to build our prototype. And what you see here is a very, what I would call a typical organization of a streaming application, where we have an ingestion step where we ingest the data from different types of sources, in this case from the IoT platform service to get our device event, followed by a Streams application that will do the actual analysis. And following the analysis, there are different actions to be taken, and you could write a set of operators or an application to handle the action that results from the analysis. So in our case here, the first application here ingests the device events made available from the connector application, the pre-built connection application that I mentioned earlier. We then perform the analysis, and then off the command goes, the decisions made, off it goes to send the command back to the device. So if we take a closer look at the ingestion application here, this is made up of a number of operators, and these operators are available in the toolkit that I mentioned, the Streams X IoT toolkit. What it helps you to do is it provides operators that will let you subscribe to event from a particular device. So here is a subscribe operator that will get the information from the device. And if you remember what Samantha had shown, it's the device event. The device data comes in JSON format, and we have another operator here that can extract the data, the application data from the device event information in JSON format. And then what I have done here is I have an export operator that makes, so once extracted, we make the application data available in the Streams tuple format, which I then export and make available to any Streams application that's interested in working with that data. So then you will see that here I have my actual analytics application here connects to that export operator by importing the data that is being made available, the device event data. And if you've noticed in the demo that Kendrick did, we have 2 types of weather information. We can either get information for real from the Watson Insights for Weather service, or we had a weather god that simulated the weather. So here we have an operator that checks with the UI where the weather god resides to see whether we should be using real weather or simulated weather. So based on that, the routing of that, we route it either to an operator that will actually query the Watson Insights for weather API to get real weather information, or we get the simulated weather from the weather god. With that weather information, we flow it further downstream, where we check simulated business rules to determine whether there is any government bans on water bans that should be enforced. So pulling all of that together, a decision is made whether the sprinkler can be turned on or not. So as you